Go ahead and get started. And so I'm the moderator for this session, T.S. Kelso. You probably heard from me this morning. And we've got 8 panelists that are going to discuss. So we're a little time challenged. So we're going to try to keep this on track. So we're going to minimize, some of the introductions and everything. So I apologize. The first presenter had to withdraw the paper. So we're starting with the second presentation by Diva Arul Daniel on ISRO's activities towards sustainable space operations, past, present, and future.
I think this is the wrong presentation.
So we seem to have a different organization on the online version of the final agenda than what's in the printed version. So I'm not sure if what you're showing on the slides is in line with what's in the printed version, which is how we have people organized up here right now. So if you're trying to find that presentation based on the previous organization, it would be the third one in line. So number 3.
Thank you, Dr. Kelso. It's an honor to be on your panel. You're like the godfather of SSA data. So it's an honor, really. So the author, Bulbul Mukherjee, couldn't be here. Actually, my name is Daniel. I'll be presenting about ISRO's activities towards sustainable space operations. And ISRO's goal is to harness the space technology for national development. It has always been that goal. In our launches, in our satellites, we haven't deviated from that primary goal. And ISRO is committed to safe and sustainable space operations. So India has actively participated in all the debris mitigations. It is a member of all the committees. It has participated in annual meetings, and most of the IADC recommendations on space debris mitigation has been followed by ISRO, and with increasingly better compliance with IADC guidelines. So this is our activity at present. Observation facilities, we have just started observation facilities. We have a radar, but it is mainly used for tracking launch vehicles during separation and other things. It is not mainly used for debris, but it is getting upgraded for debris tracking. And we have a couple of telescopes. It was for a different purpose, for satellite laser ranging, but we have kind of hijacked the telescopes. So we are trying to utilize all existing facilities in ISRO and try to build on top of it. And in analysis, we do space proximity analysis every day for our spacecrafts and collision avoidance analysis before each launch. and we contribute to IADC's annual re-entry campaigns. And we do have some modeling and analysis, breakup modeling and analysis. And mitigation, after the PSLV upper stage breakup, we started passivation of the launch vehicle upper stage and post-mission disposal for geosatellites, limited release of our operational debris. We have just two debris per launch. That is the upper rocket body and the the intermediate housing. So avoidance maneuvers are executed whenever there's a conjunction, it's executed. So one of the objectives is limited release of mission-related objects, except for the adapter. That's what I was saying. The payload adapter and the launch vehicle upper stage, we don't inject any debris into space. And during ascent phase, there's no operational debris. And all failure modes of systems are analyzed to avoid any malfunction of propulsion system. And after post-mission orbital, that is mitigation, is also done. All GSLV rocket bodies in GTO have less than 5 years life, that is the GTO objects, and deorbiting of LEO satellites at the end of life. And all PSLV rocket bodies have, at present it is greater than 25 years, but we are thinking of bringing it much lesser than that. So this was after the unfortunate PSLV destruction, upper stage explosion. So since 2002, we are venting the propellant tanks. We are doing electrical passivation, and all cryogenic upper stage are passivated for GSLV and GSLV Mark III. And post-mission disposal for geosatellites are carried out regularly, and careful planning of mitigation of service and replacement before reorbiting. And multiple burns are executed, exit from the co-location constellation, alternate perigee and apogee burn to make it a circular supersynchronous orbit. So this is for the geo spacecraft passivation. Post reorbiting and after the orbit is made supersynchronous, there is battery discharge. There is at present there is no disconnection of electric solar panel to the battery, so it keeps recharging. So we do some, we switch on some heaters to electrically passivate it, and of course after the end of the post-mission disposal, the transmitters are switched off. So this is the conjunction assessment, daily proximity analysis of operational LEO and GEO satellites with other space objects. In case of any proximity with the debris, we do a maneuver, and C-SPOC alerts are analyzed independently with more accurate state vectors from our operational satellite, and collision avoidance maneuvers are carried out based on analysis. This is for the launch vehicle. So before each launch, we, with the planned maneuver, planned trajectory, we do a collision analysis before it is cleared. So this is one of the activities which is done for each launch. This is the current system we have in place. It's in the launch port, Sriharikota, and it's capable of tracking 50 centimeter dimension at 50 centimeter cube at about 800 kilometer range. It is not much, so we plan to upgrade it, and it is just used for tracking rocket bodies and successful separation of rocket bodies, stage separations. And this is the optical telescope, which is part of SLR, satellite laser ranging system. But at present we have taken over the facility, and we intend to use it for space debris tracking. And apart from this, we have a couple of more facilities coming up. This is one of the projects which is initiated, Netra. Netra means eye in Sanskrit. So it is Network for Space Object Tracking and Analysis. It's one of the new projects which is coming up. And I'll just go to the project. So you know that ISRO operates on a very small budget. So SSA is like the last thing anybody has in mind. So to getting money for SSA is really tough. So, but still we have managed to get. So it is a big thing, and out of it we are planning to put one radar and one optical telescope. One radar capable of tracking CubeSat in 2,500 kilometer orbit, and the bidding has started. Tender is already released, and for the optical telescope also we are planning one facility and a control center in Bangalore. The work has already started, and it's almost in the completion stages. So we'll be there's plan to recruit about 85 people to work exclusively for SSA. So from 0 2 years back to such a big number of people working on SSA is really a big thing. That too, getting money out of launch vehicle programs and satellite programs is a big deal. They are the sharks. So it's like taking a bite out of the shark food. So finally to end, transforming IADC space debris mitigation guidelines into more detailed engineering practices. As of now, not many satellites have the provision to have a post-mission disposal. So we are trying to build it into the satellite design so that post-mission disposal can be done. Usually in ISRO, we try to bleed the satellite till the last drop. So there's no propellant left, and at the end of the stage, end of the mission, there's nothing you can do with the satellite. So that is slowly changing. So we are making fuel budget and other provisions for post-mission disposal. So that is a big design change that is designed for demise. And shielding work has also started. Previously, there was no shielding activities in ISRO. So now we have started shielding activities. That is for the manned mission also. It's a big thing. So that has taken up in a big way. And actually, the directorate was created just 2 years back. So we have just started talking to people, and we intend to build more observation facilities and get into data sharing agreements with people. So if you have any queries, that's the person to contact. And I hope you got that subtext in the presentation. I can't tell you openly. So that's the person you have to catch for any other queries. Thank you.
Okay, so our next speaker is going to be Chuck Dickey. He's talking about three-country trusted broker, an effective public-private model for orbital debris remediation, Part 2.
Godfather. About a year and a half ago, I formed a company called TCTB. Just a brief introduction to the company. The acronym stands for Three Country Trusted Broker, which is the business model in four words. It proposes to remediate high-mass debris in LEO owned by Russia, owned legally in a legal sense by Russia, China, and the U.S. It's a private entity. I think of it a little bit like the Red Cross, a little bit like a mediator. I wouldn't use the word marriage broker with respect to those three countries, but it's a little bit like that. So the first paper, T.S. mentioned part 2. Part 2 should be in your program material. I'm not sure if it is, but if it isn't, you can find it on my website, threecountrytrustedbroker.com. All I can say there is it's good to have young children who know computers, because I got a lot of help from my son in setting the website up. But part 1 was delivered at IAC in Washington, D.C., and described the business model and why a public-private model would make sense with respect to the three countries involved and the difficulties they would have in working together through diplomatic channels to remediate debris. Part 2 talks about the contracting phases, the procurement planning phases that will have to be accomplished before remediation can happen. And then Part 3 is scheduled for GLEX in St. Petersburg later this year, and I'm planning to roll out or to describe what's already on the website, but describes the clauses, the agreements that would have to be in place among the three countries to be able to accomplish ADR. So to get at the point why planning is important now, I would throw out this thought experiment, which is kind of a factual baseline with where we are from a technical standpoint. There are about 1,000, it's a notional number, it's probably closer to 1,200, high-mass derelict objects in LEO that need to be remediated in order to reduce the probability of collisions among those objects to 0. One country's removal of its own objects would not appreciably affect those probabilities. So it needs to be a multi-country approach in some form to remediate these objects. But when you get down to, well, a couple more facts. Most of these objects, more than half of them, probably more than 2/3, are Russian, followed by the U.S. and then China, and then a few other countries like France. The other fact is that the next collision is imminent. We don't know exactly when, but statistically it's imminent. And so when you take those facts, you have to next realize that you cannot remediate at that point, even if the technology is ready. It's probably not ready yet, but even if the technology is ready, you still can't remediate until you answer some very significant fundamental questions, like what objects exactly, in what order, how many missions, what about national security issues, how will countries authorize funding, each country authorize funding separately and independently for those missions, how will the data be shared in terms of national security issues that reside either in the objects to be remediated or the technology used for the remediation? How will you select remediators? What companies will do the remediation? How will cost sharing among countries, if that is something that's set up, how will that be audited and controlled? How will disputes be resolved? What about domestic preferences? What if one country decides, I only want to use local industry to remediate my objects. Well, that's fine, but how do you get other countries to act symmetrically with that remediation effort by that one country? How will the U.S. deal with the Wolf Amendment? It's a local issue, but something that's important. And how will countries avoid introducing politics into the discussion, which, if you heard the hearing last week on STM, you heard the witnesses and the members all talk about diplomatic relations to get this started. And our witnesses and our members said, well, let's get the State Department involved because that's where diplomacy starts. The problem with diplomacy is something that the United Nations has recognized. It's something that I think, well, I covered in my first paper, but the collisions may not wait for diplomatic efforts, and that's another one of my fundamental points, is when you get this started, you need to get it started in time to prevent the next high mass on high mass collision among these 1,000 to 1,200 objects, because if you don't, after that point, a lot of technical people, including Darren McKnight, to throw out a name, will tell you that the cost of remediation will become a lot more expensive. So that's what I've been doing. I've noticed in my efforts to communicate and work with the three countries involved some of the same problems that you all have experienced in getting STM data, for example, from China and Russia. Google Translate is a wonderful tool, but it's not perfect by any means. I think the other point I would make from the hearings last week is that the United States clearly recognizes now that international ADR is necessary, and they seem headed towards formal diplomacy among the involved countries. But within the U.S., no agency has been selected yet to pursue those efforts. So when I sent my contracting proposal in May of last year to the U.S., I sent it to Scott Pace at the National Security NSC. I sent it to NASA, and I sent it to Commerce. And I still don't have an answer for who would the contracting agency be within the government. I would make one other point about the statistics that I heard earlier today. ESA is planning to remediate ENVISAT. They've got some technology programs planned. The last data point I saw was that they expect to do a test program no earlier than 2025. That's a long way off when you think about collisions being imminent. But the other point I'm making about that remediation is that even if it was successful alone, one country, it's France actually that owns the satellite. But even if they were successful, removing one high mass object from LEO, even the highest mass object, would not appreciably reduce the probabilities of collisions among the remaining objects. So given a choice between formal diplomacy and private initiative, I think for me it will be hard for me to convince Ford to ride in a Ferrari, even if my car is faster. But that's kind of where I'm at in a nutshell. I'm making some progress in China very recently. I'm looking for local brokers in Russia and China because I've run into an issue with trust. How can Russians and how can Chinese trust someone who used to work for the defense industry? I was formerly Deputy General Counsel for Lockheed Martin Space. But trust is an important element, and finding local fellow brokers is one way that I have started to try to do that. But I will stop there, and that's TCTB. Thank you.
So our next speaker is Miles Lifson, and he's going to talk about low Earth orbit traffic management through slotting.
Thank you, TS. And so, as he mentioned, I'll be talking to you about work that our lab, the Space Systems Lab at MIT, has been doing with some collaborators, looking at what a potential slotting system might start to look like with slots designed to avoid conjunctions in LEO. Before I begin, I just want to acknowledge the co-authors on this work, especially Dr. David Arnas, who's the first author on a paper that we recently submitted on some of this work. So I won't really belabor these trends. We've been hearing about all day, but we're seeing increases in launch and more complicated behavior by launching spacecraft, large numbers of satellites, and increasing numbers of satellites, often by multiple operators being launched on a single rocket, more nations operating in space and more new actors, and then also explosion of proposals, not all of which will be built, but at least a large number of which probably will, for mega constellations, all leading to a significant increase in the complexity of the space environment. And so we wanted to ask, what could the potential role of slotting be to help address this as a tool for space traffic coordination and management? And in this presentation, I'm going to talk to you about some of the initial work we've done looking at what capacity could look like under a slotted system, some of the assumptions needed to be made for some of this analysis, and then some of the different trade-offs that we're surfacing in the analysis that we've done. So before I get into the details of our proposal, I think it's useful to talk a little bit about the idea of why slotting. We've heard a lot today about how the space environment is a global commons, and it is used by all, but obviously there's an incentive to have rational and efficient use of that commons. So we can imagine what a parking lot might look like if rather than spaces, we had people parking wherever they want in that orbit, and slotting is one way to help manage the trade-off between overall system efficiency and the ability for individual entities to do what they wish in the environment. And one aspect of that that really comes in and is attractive for the space traffic coordination and management is potentially significantly simplifying traffic management rules, which is an area that we all recognize is important, but something that I think that there still needs to be a lot more work on. And then also, and I'm excited to see the next presentation because it gets to the same question, but slotting provides one way to help get to some rigorous and quantitative ideas of efficiency and different levels of trade-off between system-level efficiency and the freedom for individual operators to operate in different manners. And then I'll just note that slotting isn't entirely new in the space domain. Slotting happens for spectrum at GEO, and then also there are proposals in the literature specifically for slotting for sun-synchronous orbits, and we're kind of expanding this prior work. So the tool we're using to generate our slotting system is flower constellation theory. It's really useful for this because some of the mathematical properties, it helps us with guarantees about both exhaustion in our search, mathematical proof that our slots won't collide with each other, as well as computational efficiency. Flower constellation theory contains as subsets most of the popular constellation designs you've heard about, the uniform ones, so Walker constellation, Streets of Coverage, Dufour, and Drame constellations are all subsets that can be considered using the flower constellation theory. Right now, we're using a technique called 2D lattice flower constellation that generates uniform orbits like this, but I'll talk a little bit about how we intend to expand that in future work. So before we can get into actually describing the slots that we've generated, I want to talk a little bit about how we're defining the problem. So we need to define a set of slots that are three-dimensional regions of space that can potentially change over time, and they need to be separated from each other so they don't collide, and that they're separated further by some minimum separation distance that's set up by the system architect. We also, because we want our slotting system to be minimally burdensome, we need to make sure that it's feasible for satellites to station keep to maintain themselves within the slots that are generated. And lastly, we want to make sure that common reference missions that could occur without a slotting system are also possible under a slotted approach. If you don't have these criteria, then you might have an interesting idea, but then kind of what's the point? And then the approach we're taking in this work to do that is to generate concentric spherical shells, because the vast majority of satellites are placed into circular or near circular orbits. We first solve those under a Keplerian model, and then we can model the maximum perturbation that a satellite in that slot could experience over some system architect defined period, the maximum period between maneuvers, and then we can size the slots and their separation accordingly. And then once you've solved this for one shell, you can go and then solve it for subsequent shells above or below, subject to the first constraint. So the technique, as I mentioned earlier, that we're using is flower constellation theory, and specifically 2D last flower constellations. So we're distributing the slots within a space of relative right ascension of the ascending node and the mean anomaly. And then you can see on the right-hand side of the slide some of the reduction we're seeing in the computational efficiency, or increase in the computational efficiency of the checking. And right now, this is all looking at the uniform 2D last flower constellations, but in future work, we both intend to investigate a different formulation known as necklace constellations, which allow us to introduce non-uniformities into the slotting structure, as well as four-dimensional constellations to investigate what the consequences would be and how feasible it is to include elliptical orbits and and relax the spherical assumption that we have in the current work. On this next slide, you can see three approaches that we evaluated, with a trade-off between the amount of freedom for the placement in the slot for the operator versus the overall capacity of the system. The top center has a random approach where, subject only to the separation constraint, it has the lowest capacity but the most freedom on placement. On the bottom right, from my perspective, left from your perspective, you can see a single lattice flower constellation, and then on the bottom right, you can see the approach of two stacked last flower constellations. We can stack an arbitrary number. It just depends on what the architect would choose. Here you can see the same three approaches, but just in a flat projection rather than a toroidal projection. And then here I have some examples of the number of slots we're able to generate per shell. The important thing isn't the specific numbers on the slide, which really are dependent on the assumptions, but some of the trade-offs that we can see. So the first is there's a significant sensitivity to the size of your slot, which makes sense. The number of potential slots scales with 1 over the square of the minimum separation distance. Another significant impact is the inclination, and for reasons I'll talk about in the next slide, we need to pick one particular inclination for each of the shell, and that's easily the most burdensome constraint of this approach, but something we think is still manageable. But so the closer your inclination is to about 46 degrees, the more slots you can fit, versus the closer you are to equatorial or polar orbits, the fewer that you can fit. And then lastly, between those three approaches, you again have a trade-off between flexibility and overall capacity. So you can do a rough back-of-the-envelope calculation based on assumptions for minimum separation distance and the number of slots, and then you're generating somewhere on the order of millions of potential slots throughout the LEO region. It really depends heavily based on the assumptions that you make. One other important factor is choosing how many of your layers you want to be parking orbits where satellites spend most of their time, versus how many you want to leave relatively free for the ability to conduct phasing maneuvers and other things in between the layers. So there's a few key caveats that we've surfaced looking at this work. The first is, because of non-spherical Earth effects, and specifically J2, we really have to have one inclination per shell. Otherwise, the propulsion requirements for satellites get prohibitive quickly, and you destroy the slotting arrangement. Another is that this slotting arrangement can deal with the rapid increase in active satellites, but we do require station keeping, and so this structure can't accommodate debris objects or inactive satellites. Those would need to be accommodated through traditional collision avoidance maneuvers. And then lastly, the slots can be designed to be compatible with existing constellations that avoid self-conjunctions, but you can't be compatible with multiple non-compatible satellites currently up there, so there would be somewhat of an optimization exercise based on the existing traffic at a given altitude. I'll also add that you don't necessarily need to have only one satellite per slot or keep a satellite in one slot, but then you would have to return that coordination to the specific operators involved within those slots if you wanted to do multiple stacking, kind of like what happens at GEO now. A few design considerations is the slot size impacts the trade-off between capacity and how frequently you require maneuvers. Capacity and maneuverability depending on how many parking versus orbital layers you have. And then also mechanisms for some kind of system architect or architects to choose what kind of inclination per shell, the slot generation strategy you want to use, and how to allocate slots themselves. I'll also just add that when you're thinking about this, there's a lot of questions that involve both policy and technical details, and it's really going to take, if this is something the community is interested in exploring, a collaborative approach. So right now we have a lot of mega constellations that are being authorized, and they have exquisite maneuvers designed to make them self-compatible, but I think a broader approach looking at LEO as a system-level problem is necessary. We've proposed initial proposal for the LEO slotting problem, and then demonstrated an approach to generate slots that would allow for this, and talked about some of the trade-offs we recognize. We're working to further develop this theory, including how to launch into very congested orbits with many slots occupied, generalizing the theory, and analyzing special orbits, and then also demonstrating concepts of operations for common behaviors under a slotted system. Thank you.
Our next speaker is Sten Lemons. Environment capacity is high-level driver for space traffic management. Sorry about that.
That's all right. Good afternoon, everyone. Thanks for having me here. And thanks for the previous presenter as an excellent introduction to what I want to say here. So when I talk about space traffic management, one of the questions which comes to my mind, which we should try to address, is what is actually safety? What's the safe distance in space? How do we make sure we can keep operating all together? And how can we enable some of the concepts as we just seen before? So I'm going to preach to the choir, but it's a fundamental thing. So I assume for everything what follows that I can count that you're on the same page as I am, meaning that an orbit is a shared and a limited resource. Now, I do this because in a previous life before running in here, I was a mathematician, and there's something which law and mathematics have in common, and that is you have to start with assumptions, you have to start at a common understanding, otherwise the whole system breaks down. So, starting from this very simple point, if I have a finite resource, the question is, how do I manage it? How do I maintain it? And I actually don't want to reinvent the wheel. I first want to have a little look of what is already out there. So there's in spaceflight for the past 60 years and way before that, there's one resource which we have been trying to manage very, very strictly, and this is frequencies. It's the spectrums we all use to communicate from Earth to ground and make use of all our daily commodities. And the other one on the left-hand side, or right-hand side for you, will be outer space itself. So I'll just highlight a few differences and commonalities on how we have been dealing with this, just to set the pace. So when we talk ITU Constitution, there's a fantastic article, it's Article 44, which essentially says that radio frequencies and satellite orbits are a limited national resource, as clearly as this. When I look into the Outer Space Treaty, we're much more vaguer. We state that exploration should be free for all state parties as long as they happen in conformity with international regulations. Back to the ITU world, if we go a bit more in depth on what they mean with this resource, we see that the ITU Constitution created an entire body which has regulatory capabilities on how to manage this resource. Afterwards, they leave the implementation to the state level, but there are radio regulations set by the ITU himself. On the other hand, Outer Space Treaty, states retain jurisdiction and control over what their members do, but it doesn't go further than that. Lastly, the ITU specifies that you have to have a rational, efficient, economical use of your resource, and it requires equitable access. On the outer space treaty level, you're left with, okay, avoid harmful contamination, and where necessary, maybe adopt some countermeasures. That's where we are. Of course, both of them are created in different times with different benefits, but it paints the picture. A bit more practically, why do we have ITU regulations? Well, because we have something like interference, radio waves, they don't stop at natural borders, they cause interference if you don't manage them appropriately. And how to do that is laid out in the radio regulations treaties. On space debris level, on the outer space front, let's say, you have space debris mitigation policies, which are loosely coordinated across the globe, actually far more effective than one would assume from a loose cooperation, but they're policies which can be set. This means that, again, on ITU side, there's a strict procedure on how to do allocation, how to design the power of your satellite, and what the rights and obligations are if you launch, which means also planning, allocations of blocks, coordination. On the space debris side, yeah, if you have a collision between two operators, there's best effort coordination to avoid this collision, first of all. And there's the ever-growing adoption of soft law practices, which gives this kind of space debris mitigation policies more of a law-like feeling, because, for example, when you want to launch into space, you might have to demonstrate that you are compliant with certain standards. That's it. Now, how do we get out from there? So, first of all, if we want to make the ITU analogy, we have to talk about interference. Now, for outer space and space debris specifically, interference is caused by three very specific categories. First of all, on the left-hand side, if your satellite explodes because your battery isn't passivated, because there's an ignition in the tank, you're going to create a lot of debris. It's something that you should not do by design. First source of debris. Secondly, you might be perfectly passivated, but you might collide with another object. This can be an ASAT test. This can be two objects which you could see and you deemed that the risk was not high enough. But it can also be a collision with an object you could not see, which is below the current space surveillance limits. It can still break up your satellites. And thirdly, a great source of debris nowadays is that we do not remove our objects from the orbits they're occupying. There's a bit of a trend, and you can read these details peacefully in the paper, but in essence, we're still very good at leaving most of our stuff behind in orbit, especially in LEO. Now, this has, again, three consequences. Oops, sorry. First of all, if I create interference based on these processes, I have a short-term consequence. If an object gets stranded, if an object explodes, the first one who's going to be affected by those ones are your orbital neighbors. Everybody around you all of a sudden will start to have to avoid the debris you caused. You can think about the recent ASAT, but just a satellite which stranded will just decay from orbit and cross many people's path. Just one example I want to give of that, and I'm not sure if the laser works, so not. So there's lots of colors there. As TS mentioned, not everybody likes numbers, so I use colors, but it might have a similar problem. So you see in the last bar, 2009, that there's an increase in dark blue and medium-sized blue. What I've counted there is how many times one of my fleet, so ESA satellites in low Earth orbit, had to avoid a satellite or piece of debris of a certain type. And after the new space revolution takes up, what do I see is that all of a sudden 25% of my close approaches, which I can see, are due to small satellite and constellation objects, which did not used to be there before. So just by changing traffic, I have to account for other people acting in my orbital vicinity. Secondly, I have midterms effect. If I put policies in place, like space debris mitigation, for example, the 25-year rule in LEO, that you have to do post-mission disposal after your mission is over, I should not expect that also the environment, or be surprised that the environment in which I operate is changing. So after a while, what you see is that also the injection orbits that operators are using are now starting to be compliant with 25 years decay time after end of mission. So I see an increased amount of traffic to a zone around 600 kilometers in altitude. That's not bad by itself. It's just something that any type of interference theory needs to be able to account for. The same is even exacerbated when you talk about a large constellation. All of a sudden, there's going to be orbits which are very dense and actively used. And one question which then comes for space traffic management or for space safety in general is from, okay, I also have a mission who wants to go to the same orbital regime. How close can I safely operate near a constellation without causing interference, neither for them nor for myself? And then there's obviously the long-term space debris mitigation policies are there because they want to protect the environment of a Kessler syndrome. Any objects, whether it's one or whether it's a constellation with thousands of satellites using 20s or hundreds of launches to get there, with a fixed amount of operational time, has a certain, let's say, contribution to the long-term sustainability of space. No mission can be environmentally neutral. There's always the risk that your satellite gets stranded. There's always the risk that you get hit by a piece of debris which you could not track and hence still creates a fragmentation cloud to you. We should not underestimate that. Good. So what do I want to do? I want to define an interference criteria and I want to use it in a practical sense. And the simplest way, at least to my knowledge, to do this is to cast the whole problem as a risk. Simply probability times severity. I want to know what is the likelihood of a certain event, a catastrophic collision, to take place in a certain year. And as a severity or as an effect term, I want to know what is the effect of this event on my orbital neighbors. How are they going to have to increase their collision avoidance capabilities? Or in the worst case, would they have to start using another orbit in order to perform their missions? So it's the second step in the sense from previous, let's say, regulations, policies. They always say get yourself out of orbit, do collision avoidance, always formulated from the point of view that you are an actor and that you try to keep everybody safe from your own actions. Now I want to quantify what your consequence of your actions is. So this requires lots of things. First of all, you need a crystal ball because you need to be able to predict what everybody else is going to be doing, which is tough. Next to the classical problems of covariance propagation, risk assessment, knowing what happens, what's the transparenting, what's my other objects doing, how massive are they, etc. Yeah. But in essence, it's physics. So I'm not going to go through the formulation. That was when I was still assuming that I had 15 minutes for this. But just to give you a feeling for this, you get a whole bunch of freedom. So depending on what your satellite is, the consequence of fragmenting is higher or lower, also depending where it flies. And whether you do this in a large constellation or not also has an effect on how you affect the environment afterwards. So I will not go in details. You can read it in the paper if you want. But now take from me that you have a way of quantifying what the interference is. The last point I want to do then is to say, okay, so in any given year, for any given object, I know what their potential of interfering with the environment is. That's great because then on the bottom right, I can integrate this out for all objects which are in the environment at that point in time. And I can check if this risk is actually compatible with an evolution of the environment which triggers or not triggers a Kessler syndrome. I have a numerical way of capping what kind of risk we're taking with respect to triggering the Kessler syndrome. And that's the point I want to reach because that's where you're effectively in the same state as an ITU type of setup. You know how much interference you can tolerate and you know how to quantify that. So let me bring you to the last slide. So interference itself, or just based on the concept that space is a limited resource, or the orbit is a limited resource, you have two sets of risks, short-term and long-term. But as long as you quantify this, you get to this notion of a capacity figure. On any given year, I know what full means, and I can tell you when it's full. And based on that, it's also possible to define what a reasonable access procedure is. That means indeed that before you launch, you have to transparently communicate what are your intentions, how many objects, where are you going to fly them, how long are you going to fly them, because it might affect somebody else's plan to go to a similar location. But such a system exists. The ITU has been doing it for 60 years. So if we play out this notion of an ITU model, we can see that access to space, where you fly, is the first step which you can implement in a global space traffic model, because it can help keep everything safe, at least in this model. Thank you very much.
Right, our next speaker is George Anthony Long, and he's going to talk about the duty to disseminate space weather forecasts.
Good afternoon. My name is George Anthony Long. I'm not a meteorologist. I'm not a scientist. I'm not an engineer. I'm just a lawyer who's here to talk with you a few minutes about the weather. I thought I had a slide presentation. Now, when we talk about the weather, here we're not talking about terrestrial weather as much as we are talking about space weather. And we all might decide, why does it matter? Why does it impact us? And why is there any concern if there's a duty to even disclose a forecast? Okay. Oh, yeah. Oh, yeah. Because, I mean, with the weather, it's sort of like with space here. We talk of the duty to disseminate. Now, what do we mean by duty? When I use the word duty, what I'm referring to is an international legal obligation. Now, why does that matter? It's because if there is an international legal obligation for a state to do an act, then that imposes state responsibility. And if a state breaches its responsibility under international law, then arguably international law makes the state liable to pay reparations to foreign nationals and other states that have suffered harm flowing from the breach of that duty. So the question is there such a legal duty with space weather? Before we do a look at the duty, first let's talk about what is space weather. Okay. Space weather, as defined by the NOAA Space Weather Prediction Center, it's conditions on the sun and solar wind that, importantly, can influence the performance. Not does influence, but can influence. And what goes to technological systems, and that can affect human life and health. So what we're talking about, not that it does, we're talking about an event that has the possibility. Now, how much of a possibility? That's undecided, that's unexplored ground. But now, this definition is not totally comprehensive, because space weather can include things that aren't affected by solar events, such as meteorites or meteor showers and cosmic radiation. Cosmic radiation is radiation that exists that's not caused by the sun. But now, when we get to the solar events or activity on the sun, these are the three basic type of events that can result. You have solar events can cause electrostatic discharge, which basically will only affect satellites. Okay? It will only affect things that are in orbit, space assets. Then you get to things like geomagnetic storms. Those not only affect satellites, but they also can affect terrestrial technological systems. And they are categorized, just like we do typhoons, by from 1 to 5. And then you have solar radiation storms. We all know the dangers of radiation, and that, of course, they are also classified from 1 to 5. But now, when we do the main event, before we get to geomagnetic storms, is that with respect to solar radiation, For some reason, radiation is more intense around the polar regions of the planet as opposed to others. I don't understand the science behind it as to why the Earth's magnetic shield doesn't deflect radiation as much from the polar region as it does from the other areas of the Earth. But why that is critical, or why that is concern of people, is in the aviation industry with respect to planes that fly polar routes. Because the airline industry has really taken a very proactive approach within its own industry of being aware of space weather as it affects radiation. Because, one, the health and safety of its flight crews, as well as the health and safety of passengers, can be at risk based on the amount of radiation that can be exposed to based on a solar event. And airlines will reroute flights if it's determined the solar radiation or cosmic radiation over a particular polar region is perhaps too great for a human to be exposed to. And that does occur on occasion. But the main aspect, I think, that would catch the attention of most people as to why space weather matters is what we call geomagnetic storms. And what geomagnetic storms do, they not only affect objects in space, but they affect technological systems on Earth, whether they're power grids or telegraphs, telephone lines, and things of that nature. Now, the most powerful or the strongest geomagnetic storm known to have hit Earth happened in 1859, known as the Carrington event. Now, if we understand, this is at the infancy of the technological age. At that point, the real only true technology that existed was the telegraph. And what the Carrington event did was that it electrified the telegraph system, caused telegraph operators to become shocked, telegraph paper to just simultaneously combust, and made the systems totally unusable. Now, it is estimated and predicted that if that magnitude of a storm struck Earth today, and given our dependency and addiction to technology and technological systems, the damages would be at least $1 trillion. So that is the necessity of being aware of space weather and how it can potentially affect terrestrial events as well as objects and people in space. But now let's look at if there is a duty to disseminate. And what the duty is, we start with the Outer Space Treaty. Let's look at Article 5. A state has a duty to immediately inform if there's any phenomena in outer space or a celestial body which could jeopardize the life or health of astronauts. Now, I'll submit that any of the space events we've talked about, whether it's an electrostatic discharge, a geomagnetic storm, or radiation storms, can affect the life and health of an astronaut who is in space. So that in and of itself creates, arguably, a legal duty to disseminate or disclose that information if it is known by a state. Then you can go back to Article 9 of the Outer Space Treaty, which imposes the duty to inform if the results of space activities. Now, the sun is studied by satellites in space. That's how the sun is measured, and we keep track of solar weather a lot, is by satellites in space. So that is arguably a space activity. So essentially you can make the argument that the results or your possibilities or your forecasts based on studying of the sun and the solar events creates a duty to inform. So what you learn from that has to be disclosed and informed. Lastly, Article 1, where it states that space, the use, is for the benefit and the interest of all countries. All countries would have an interest if there's a geomagnetic storm approaching, or that will hit, or that can possibly occur. So the argument exists that Article 1 also imposes a legal obligation for states to disclose space weather forecasts if it is known. What this leads to is that assuming that there is a legal duty, what does it mean by dissemination? What does the informing result in? For instance, you can go to the Space Weather Prediction Center website, and it gives space weather forecasts. All right? But I mean, I can go there. I don't necessarily understand what it means, but it's there. Is that sufficient to satisfy an international legal duty? I don't know the answer to that question. Hopefully, we never will have to address that question. But I would suggest that to satisfy your duty, it must be not in the language or the lingo of the industry, but something that those of us who are not involved in the industry can understand and comprehend. And then there comes the duty or the obligation of how much forecast or how foreseeable, the foreseeability issue, in the sense that given the time it takes for energized particles or winds to flow from the sun to the earth, how much time in advance should there be to forecast or to warn other countries? And those are unexamined, unknown legal questions that I assume may and hopefully will not arise in connection with space weather. Thank you very much.
Okay, our next presenter is my co-author on a paper about Starlink, and I'll let him get to it. Dan Altroghi.
Thank you. Great to be here. Our talk is actually not about Starlink. It's about potential degradations to SSA due to a large constellation. Starlink happens to be a convenient and ready one to examine that with, so that's the tie there. This is part 2. There was a paper we presented at DC at the IAA SSA conference in January, and this extends that work a little bit. The goal is, like on the picture on the right, to examine what happens when you have large constellations that are optically tracked, and you have either tracking mode or the streaking stare modes. You get degradation to the images. Now, we have at our count 58,146 applications for satellites, large constellation satellites. And granted, we probably won't see those. Probably maybe between 5 and 50% will actually come to fruition. But even if that's all that comes to fruition, that's still a tenfold increase likely over the next 10 years over what we have today. So we did pick Starlink. I show the constellation there. It's 1584 satellites, 53 degrees, 24 planes. The orbit was initially applied for at 1150, and it since was lowered to 550. And there's very good reason for that with orbit lifetime and sustainability and so forth. And there's also a checkout orbit at 350. That aligns very well with best practices of checking out a bunch of satellites, especially a new design at a lower altitude, and then raising it up. Unfortunately, when you do that, the satellites are a lot closer to the optical sites, so they're a lot brighter. And this is a video just of the starlight satellites. You can see they're quite bright. What I realized when I was walking through a city as a huge jet plane flew right across my vision is there was a time where we didn't have planes either. and people have gotten used to those now. This is in the paper. This is actually from our first paper, so I'm not going to go into detail, but we did develop a rudimentary brightness model of the Starlink satellites for the purpose of this study. Now, where does this degradation happen, or where can it occur? Well, it turns out it's at the terminator conditions. And so the ground site, to be an optical site and track, generally needs to be in darkness past nautical twilight. The satellites that it's seeing, if they're in the sun, not in dark yet, that's when they're very bright to that site. In our case, I'm interested in what you oftentimes apply telescopes for, is tracking geo regime. And so the belt, geo belt, from like minus 15 to plus 15 degrees latitude. There's also a huge impact, potential impact, to the astronomy community. This is an image where you can see a galaxy at the bottom, just the left side there. That's an enlargement of one of the other picture, which is a full frame, taken at the Goto Observatory. So especially wide field of view sensors and long exposures, that's where the most susceptibility happens. There are mitigation strategies. You can look to make your satellites darker. That's something that SpaceX has been trying. You can optimize your shape and dimensions to minimize the reflected surface. You could control your attitude maybe to not reflect as much. And you can also select large constellation orbits that are further away. So there's kind of a struggle there to go higher to decrease overall brightness, or lower altitude to reduce the duration of the interference and also have a shorter lifetime. So this is some of our parametric studies. It's in the paper. Just to orient you, though, very quickly, the upper left picture shows in a right ascension declination space where the large constellation can be, so that it has the potential to interfere with a ground site that's looking at geo belt. The right side is where the ground observer could be. That's interfered with that. And then the bottom one here are the geo belt locations that ground site might have been looking at that would then be degraded. So there's three different pictures, and I put some cartoon Earths here just to kind of show you what's going on. The sun is here. This happens to be a vernal equinox I simulated. And so here's the Earth. So we're on the dark side of the Earth for these guys, the ground observer, and it's near, again, those terminators where the large constellation could impact things. If you coat the body, and I'm going to flip back and forth, you can see these colors. That's the scale of visual magnitude. So actually, as it gets darker, like that, you can see that this coating, in theory, can make a difference, maybe 1 to 2 orders of visual magnitudes. This is what happens in the summer solstice. You can see the sun is in the northern hemisphere now, and you can see that distorts the shapes, but you're still around the terminators. And then, again, if you coated the spacecraft body or otherwise made it darker, that helps. So this is, I'll dive right into this section too. TS Kelso's been working a lot of operations and trying to help sort out what objects are which in en masse deployments. You can see a picture he actually took up here. What time of day was that? Morning, 6 a.m. or just before sunrise, and you can see it's quite visible there. So these really are bright objects. They also pose a tracking challenge. Mass deployments involve a lot of tightly grouped objects. Typically, they're the same form factor, so making sure you associate them correctly can be very difficult. If you misassociate them or orbit tracks from them, then you end up having poor orbits, and then your safety of flight is not great. And some of these points TS made this morning as well. There is a demonstrated assignment process. I know TS works with the 18th a lot to try and sort out what objects are which. It is complicated by the low thrust spacecraft that tend to be in large constellations, in that that's harder to get a good orbit solution if you don't have crowdsourcing and maneuver plans incorporated. So there are impacts. You can get lags in your ability to get a good orbit solution, and it can be difficult to propagate forward. This here is a stomping point. So we just went through kind of part A of this briefing where we talked about large constellations' potential impact to degradation to SSA. It turns out for SSA purpose, if you know where these bright objects are, you can mask them out, just like any other star, because stars and planets are bright too, but you know where they're at. That implies some level of data sharing and cooperation amongst the operators. And also, again, in STM and this early association, once again, sharing of data and doing analysis based on the best of breed data that's available is really important. We do stand to gain or be blessed with many, many conjunctions coming up. Millions. We have a paper from mid-January, happy to share with anybody, on LEO encounter rates and collision risk. And the number of potential collisions and encounters that the operator has to sift through is going to just go very high. So we have to figure out how to get the data more precise so that we can filter out the false alarms. That's important. And again, working together is the buzz phrase. So in conclusion, we can mask large constellations for SSA purpose. There are going to be impacts to the astronomy community, undoubtedly. And some of our parametric assessment here maybe gives you a feel for the local hour angles that those sites will have to go through where they could be potentially affected. And they may have to try and cater their process to avoid those. And that's it, I think. Yes, thank you.
Okay, our next presenter is Mark Skinner. He's going to talk about techniques to mitigate initial orbit confusion for masked CubeSat launches.
Thank you, TS. Apologize, they've got too many charts for the time that we ended up getting at the very end here, but I'll try to skip through this. Let's see here. Yeah, so what do we observe to be happening? What does this lead to? What are the problems? How do we fix this? So there's different kinds of solutions. This is not a one silver bullet that's going to solve this, but there are many different ways to do this. But I think it is a tractable problem in the end. The symptom. We're launching a lot of CubeSats at once, and they're not being identified in a timely fashion. You can see from this ESA chart that the fraction of the identified CubeSats per launch does not necessarily reach one, even after months. So a number of objects are going. This is problematic because if you're a regulator, you are some people might say you're out of compliance with the Outer Space Treaty Registration Convention, because if you can't identify it, you can't register it. Talked to Steph Earle at FAA CST, and he said, yeah, we don't register things that we don't know what they are. They could be anybody's. Also, if you look at the IADC and UN COPUOS guidelines, they say, don't launch junk. So, I mean, if you want to launch junk, you can go down to the Home Depot and buy yourself a brick and launch that and be much cheaper. So things have to happen here. If you're an operator, an owner-operator of a CubeSat, maybe you're Doug Lavero's daughter is in middle school and you're launching a CubeSat, and you put a lot of effort to it. I know from personal experience, I had 5 man-years of my life go down the tubes when a Orbital Sciences Corporation launch failed, and our payload never was released. It's a different kind of problem, but I feel their pain. You put a lot of effort into this thing and it dies. Space is hard, yeah, but let's not kill things unnecessarily. Yeah, that's everyone's unhappy when this happens, right? And this is extra work for SSA STM providers, right? They don't need this. They have enough on their plate as it is, as we heard the keynote this morning. And then if you don't know whose it is, who do you contact if there's a close approach? Well, get out your Rolodex, start dialing. Ain't nobody happy. So as Dan mentioned, when you've got launching lots of similar things of the same size and shape, an NU CubeSat looks like an NU CubeSat looks like an NU CubeSat. And they're also, in the case of CubeSats, they're small, and they were designed to be at the levels of detectability. When they sat down and derived the CubeSat standard, they said, well, we can see something that's 10 centimeters by 10 centimeters by 10 centimeters, but that doesn't make it easy. That's at the sort of the minimum level that was available at the time, and in some ways still now. The CubeSat philosophy is do things fast, typically, sometimes. I mean, not all CubeSats are inexpensive and cheap. Some are very fine, like Swiss watches, but they're just highly miniaturized. But for many people, CubeSats are a way to get into space without spending a lot of money. Or you want to do some very rapid tech demo kind of thing. So people don't use, redundant systems and radiation-hardened electronics. They're flying off-the-shelf sorts of things that don't necessarily have a lot of or any space heritage or ability to withstand the orbital, all the things that go on in space. We heard the radiation environment from the sun and that sort of thing. Sometimes the designs, although we're getting to a point where we're getting more off-the-shelf things that allow for ease of design, a lot of times designs don't include fail-safe mechanisms, backdoors that can allow for mitigation when problems do arise on orbit. There's also compressed schedules. And what this leads to is a lot, as somebody at Spaceflight Industries said, he said, a lot of the stuff is one SAA passage away from a terminal latch-up. So, and that could happen within a few orbits. And as was mentioned in TS and Dan's paper, many CubeSat operators, or any operators, don't have any kind of independent means to tell which of the satellites is theirs. So, and they're all in these similar orbits. So, yes, they're small size, low cost, and they offer lots and lots of benefits. I'm not saying anything bad about CubeSats, but they do pose some unique challenges that I think we need to look at. And here's, if you're not familiar with the SAA, it's a radiation belt east of Brazil and Argentina, and you pass through there, and it can be bad. You have to take that into account. So there are some things that can be done. I mean, if you're going to be launching a CubeSat, I think it's imperative on you that you do some systems engineering and follow some guidelines and best practices for design of spacecraft without going into redundant systems and making your thing huge and expensive. But you can read some of these things here. So that is, I think, key is if you don't launch a brick, launch something that will survive and test it and make sure it's going to survive at least some initial amount of time, some minimum success criteria, to put it in NASA parlance. There's also, as TS has mentioned before in his Adelaide paper, a certain amount of coordination that needs to happen. Yes, it can be a lead a horse to water, but you can't make him drink thing, but I think that's where the regulatory aspect of things can provide that stick that will offset the carrot of what you're trying to do. So there needs to be a good interaction between the launch provider, the owner-operator, the CubeSat dispenser, the SSA, STM center. They all need to talk. They all need to be coordinated, working in the same thing, open levels of communications, common reference frames, et cetera, et cetera, et cetera. There are some dispenser, the people that consolidate these launches and provide the launches need to do some things. I'll show you a thing on that. So that you can get things out. One simple way is, well, why don't you just wait a couple orbits before you launch the next one? Then a couple orbits. Well, that gets into ground station considerations and SAA passage and those sorts of things that make it hard. So there's some pushback on that, but there are some things that can be done. And then independent ID mechanisms. So if you're a dispenser going this way, and around the Earth, and you're launching CubeSats, you launch them 2 at a time to avoid angular momentum problems. You can launch them in lots of ways that are wrong, but there's one way that it does work pretty well. If you launch them in track and behind you, then you get the CubeSats to kind of string out in a string of pearls. If you launch them in other directions, perpendicular to your motion, then you're going to get one orbit later, you're going to get bunching, or you're going to be crowd effect. You can't tell which one's which. So that is something you want to look at, and it doesn't really cost any extra. It's just how you do things. So it's sort of a best practice. One thing you can do, and this is something I've been seeing a lot, is you can use PNT-derived positions on your CubeSat. These are little cards. They're about the size of a thick credit card. There's a product that can go on the outside of a CubeSat. It's about 120 grams. Costs $13,500. It's available commercially, TRL9. And what it does is it uses GPS signals to derive a position at time. It has an ID signal. And then you use a LEO communications, existing LEO communications satellites like Globalstar or Iridium to then email your coordinates down to the ground, and you can get it. And that can work even if your satellite suffers a very early failure. So that is, I think, an exciting possibility. Another possibility, one that SRI has been working on, is RFID, radio frequency identification. I had one when I took my cat to Maui, a little grain of rice. You could pass a wand over his neck, and it would come with 16-digit code, so you knew that was my cat. But you can do the same thing with your satellite. Now, there are some details. I've been trying to get people involved in this. One of them is the band width of the radar that is needed is somewhat custom. So I'd like to get this to be an S-band radar so that Leo Labs, for example, could participate in this. But that's a bit of IRAD that has to happen on somebody's part. But this has been demonstrated. You can see the size of this thing compared to the quarter, so that can work quite well. Another very low cost in keeping with CubeSats is using small retroreflectors. If you put varying numbers on sides of a CubeSat and then you illuminate it with laser beam, you get varying returns that allow you to distinguish between one from the other. An additional benefit of this is that these can be tracked by the International Laser Ranging Service. And when you have these little retroreflectors on them, they can tell you the position of your satellite to the centimeter level, certainly the sub-meter level. So that is something for close approaches that could be quite beneficial. These things are about half-inch by half-inch by half-inch, and they cost about $150 a piece. They are available commercially from almost any optical supply store. So there's no moving parts, no batteries, nothing needed. You just need a laser on the ground, so something like EOS in Australia. There are some schemes, Elroy from Los Alamos and LEDsat from University of Michigan and University of Rome, to put a light source, a visible light source on the external to a CubeSat, allow it to flash in some sort of pattern, some sort of code. Then you're using some sort of telescope on the ground to distinguish which one's which. And by the very act of tracking it, you both get orbital information from tracking it with a telescope, and you get the ID. So this is LEDs that can help us out. So in conclusion, how can we solve this? So I've decided that I want to do more than just write a paper about this. In the course of putting this together, decided this could actually be done via a tech demo. So I'm working with the New Zealand regulator, with Rocket Labs, Leo Labs, Michigan, Los Alamos, Black Box, EOS, and Spaceflight Industries to actually do a tech demo on some upcoming consolidated launch that we could actually put some on various things, not to choose a winner, but to come up, sort of qualify all of them. So in a light touch regulatory regime, there can be a Chinese menu. The CubeSat owner, operator, designer can decide which one best fits what they need to do, what their requirements are, and choose from one of those and then put that on there. Then they'll have an independent means to do it. But the other things are necessary too. If you're launching a dead CubeSat, it doesn't matter. It's why bother? So, thank you.
Last but not least is Ruth Stillwell, who is right when it comes to the right-of-way in space.
Thank you. So I always like listening to all these panels where they talk about all of the different ways we can know where everything is. And once we know where it is, what do we do about it? I was at the World Space Forum, and I was asked a very provocative question, which is, what is the most challenging thing facing you in your work? And to me, the most challenging thing is that we all agree and nothing gets done. And I use the example of American Thanksgiving. It is very, very easy to agree that we will get together for Thanksgiving, and we all know what we'll eat. We're going to have turkey, we're going to have mashed potatoes, there's going to be stuffing. But that's not enough of an agreement for us actually to have Thanksgiving dinner. Someone has to decide who is going to host, what time it's going to be, who's cooking the turkey, and the whole thing can break down over a discussion of cranberry sauce. So agreement is harder than it looks, and it is important for us to have this agreement about norms and standards of behavior in space, and there's a lot of talk about it, and there's a lot of agreement that we need these things. So I'd like to talk about some plane crashes. And why do I want to talk about plane crashes in a space conference? And it's because aviation is widely regarded as the safest form of transportation. But it did not start as the safest form of transportation. That safety record is built on hundreds upon hundreds of plane crashes and the reactions to those crashes. And space does not have the luxury of being reactionary because our crashes stay with us and they stay in orbit as debris. So what lessons can we learn? Should I hit the right clicky button? So I want to use a very specific example. And in the aviation community, this is a well-known and well-studied crash. On July 1st of 2002, a Boeing 757 and a Tupolev 154 crashed over Oberlingen, Germany. And the reason why it's important, and an important illustration for space, is they were safe airlines. They had conscientious operators. They had professional pilots. They had operating safety nets. They were safe, certified aircraft. It was uncongested airspace in good weather. The pilots and the air traffic controller were aware that there was a conflict between these two aircraft, and they were all taking action to resolve it. The planes collided while both were executing an avoidance maneuver. Two airplanes at 36,000 feet crashed at 34,800 feet in an active descent. So what happened? These two aircraft, in approaching each other, the Boeing 757 got a resolution advisory from the onboard collision alerting system telling it to descend. The Tupolev received an advisory from the air traffic controller telling him to descend. The controller did not know that the 757 was already descending, and the Tupolev then received a resolution advisory from the onboard system telling him to climb while he was already in a descent configuration. This accident was caused by things that happened long before either pilot got in those airplanes. The integration of the standards for how TCAS would be applied in the system was inconsistent, and there was not agreement in different countries on how a pilot was to respond when he had conflicting instructions from an air traffic controller and the TCAS. The official report stated that the integration of TCAS was insufficient and did not correspond at all points with system philosophy, and that the regulations and procedures were not standardized, were incomplete, and were contradictory. And when that happened, they had a break in communications so that the three people involved in the situation did not have common information about what was occurring. So let's compare that to the recent conjunction, which did not result in a collision, between the Starlink 44 and the Aeolus ESA satellite. We were relatively uncongested, similar conditions, there were safety nets in place, and the rules were not clear. There was also communications breakdown. ESA executed the maneuver, and a collision was avoided. But without a clear understanding of who was required to execute the maneuver, we could have had either no action or both take action and had that conjunction result in a collision because our standards are not clear and our communication systems are not as reliable as they need to be in these situations. When we have no external authority making the decisions, we rely on rules to ensure the safe separation. So the question becomes, what do those rules need to be? Who was required to act in that Starlink ESA conflict? You cannot be a good actor if there are not good rules to follow. The answer to that question is we don't know who was required to act because we don't have an agreement on right-of-way. So what right-of-way is possible in space? I looked to other models, and we have some very clear models in both the aviation and maritime domains. If you look at these examples, they're both predicated on two fundamental issues. One is that the least maneuverable has the right-of-way. So a predicted conjunction in space between debris and a maneuverable satellite is easy. One of them is not going to move no matter what we do. So we know that the other one has to. It is when we have two maneuverable satellites that the question becomes unclear. So if you look at aviation, you have this very clear right-of-way based on maneuverability. The more maneuverable gives way to the others. And in maritime, we have the same, except for we bring in this element of a vessel not under command, or a vessel restricted in her ability to maneuver. And the question becomes, how do you know? Because you cannot know just by looking at the vessel that it may be restricted or not under command. So that information needs to be shared. If we have that same sort of standard with operational satellites, we need to have the information available of the health and condition of that satellite for the other operator to evaluate to determine who has right-of-way. But we don't have a rule that requires you to share it. But if we follow this model, let's be easy. Let's adopt the model in maritime and aviation and apply it to space. Have we then inadvertently created a perverse incentive to deploy a less maneuverable satellite so you get the least maneuverable advantage in maintaining your orbit? That's not a healthy state for sustainable in space. It's not that easy when we can't decide who's going to cook the turkey. So how do you know the information? How do we create a set of rules that don't create perverse incentives? But what information do we have to share? These are controversial issues, and these are difficult issues that are not easy to decide. So we know that we need standards and norms of behavior in space. And standards are hard, and standards take a lot of time, and we've talked about the role of diplomacy. In order to move forward, we need to first decide what's the most important things. What are the standards we need? If we wait to get standards for all of the operating constructs, we will have this same discussion 40 years from now and talking about the need for us all to agree. So I did take a shot at what are the few things we need to start with. What are the priorities for STM where we can start a process where we can get a framework of agreement? What standards are needed? So I bring up a few. Right-of-way, I think, is quite obvious. We already have an issue. If two maneuverable satellites are in conflict with each other, who is required to maneuver? Because it's important that we know who is required to and which one will maneuver. In all of the aviation and maritime examples, the non-maneuverer, the one who is being given way to, is required to maintain course and heading. There is an obligation on both sides, so it is a coordinated response. When we have TCAS systems on board aircraft, they communicate with each other to have a coordinated response. So that's an important element as well. Not just what are the rules, but how do we ensure that we are able to follow the rules and have sufficient information. Then the question of priority. This is often confused with right-of-way. Priority and right-of-way are not the same. In aviation, we have several different types of priority. One is first come, first served. Then the question becomes, how do you determine first? First to launch, first in the orbit, first to arrive at the point where a conjunction may be possible. What is first? Then the other example from aviation is best equipped, best served. The operator who invests the most in technology receives an advantage for that investment. Perhaps they have access to airspace first or access to preferred orbits. Is that a model that would work for space? What is the operational advantage to offset the investment that we're asking the industry to make? And then, of course, we have priorities based on who is the operator. State aircraft have priority over commercial aircraft. If we have that in space, is that acceptable? And if so, what states? How do you evaluate which state has priority over another? You can spend a lot of time debating that one. The other issue is risk tolerance. And this is a very important issue because we do not have a common standard on what triggers a maneuver. And we saw that with the ESA Starlink conflict. There was a different view on whether or not a maneuver was even required. So the International Space Station will maneuver at a 1 in 100,000 chance of collision with debris if it does not compromise the mission. At a 1 in 10,000 chance if it does compromise the mission. So what role does mission assurance play in that decision-making process? And is there a way that as a community we determine at a certain risk threshold it is not the operator's decision, because you are now assuming risk for the sustainability of the orbital environment, and who determines where that authority lies? Debris generating behavior is a very important one. If you are leaving spent objects, what are your deorbit plans? How long can we leave a defunct or derelict satellite in space, and where? Are all orbits the same? Do we have different standards for more popular orbits? This is very common in aviation as well, where access to more popular altitudes are based on your willingness to equip at a higher standard. And finally, alerting. And this is another issue that came up in the Starlink ESA conjunction, that there was a breakdown in communications, and SpaceX said that they had the glitch in their email system and did not receive the alert that the probability had increased. The way we have the alerting system designed now, the alert is sent to a designated email to receive the conjunction alert notification or the close approach notification. That's different than every other alerting system we see in safety systems. When you think of safety alerting systems, the alert generator does not chase down the individual recipients. They generate an alert to a community. That community has an obligation to monitor the alerting system. If we build an alerting system where the obligation rests with the operator and all operators have to monitor it, we avoid a problem where the alert generator doesn't have the correct information of who to contact. So I've gotten my hook playing the music. And luckily, that was my last slide. These are hard problems, but the hardest problem is if we do nothing.
All right. To do.
Okay, we've got about 10 minutes for questions.
I'm the one who's going to be handing the microphone to people. I actually have so many questions, but you know, we don't have enough hours in the day, so let.
I gotta admit, everybody's got their a mean sock game today. Mr. Long, I have a question for you about the space weather, about your presentation. I was just wondering, how might state practice influence a determination on whether or not there is a duty to report space weather? I think the space treaty's been around since, well, for a good 50 years now, and I mean, we don't really see that much use or notifications about space weather, so I'm just wondering if that is also something that would be looked at when we're trying to make a determination.
State practice is a form of customary international law that I submit will come into play only if there is no written law addressing the issue. And here you can look at how the provisions of the Outer Space Treaty. And arguably, you could say, well, there is a written provision here that covers this instance. Specifically, you talk about a phenomena in outer space or on a celestial body, which is the sun, which can endanger the life and health of an astronaut. Arguably, it's hard to say that space weather doesn't fit that criteria. So I would argue, or it could be argued, that there's written law to cover the point. But then again, you know, I'm a lawyer with lawyers. There are lawyers that can take the other side and say, oh, well, that's vague, that's not clear, so maybe we have to look at state practice. But now, since you mentioned state practice, and I'm going to wrap this up, is that states are now beginning to move towards that goal. Because the United States just recently, in March of 2019, the White House issued a space weather strategy and action plan, which basically addresses how the country will address the issue domestically, but it does recognize that there is a need to maybe adopt and coordinate internationally and develop international standards for exchanging space weather information. So to the extent that you want to say that state practice controls, now you can say that there is a beginning of state practice in this particular area, because now because of our technological addiction, countries are beginning to see the need for it.
Mariel Borowitz from Georgia Tech. Ruth, I really enjoyed your presentation. Thank you for that. I was curious, for the piece of, we have to agree what's the risk threshold, right? So there's one, what's the threshold number in these different situations, but also whose data and analysis do you believe in terms of whether you've actually reached that threshold, right? If you're thinking about the SSA data analysis. So what do you think on both of those two issues are the most likely ways forward? Can you address that on a national level and then move to the international level? How do you start to get agreement on that?
I think it's difficult to try and come up with national level regulation and then export them because you introduce political resistance. That if you can have an industry-driven standard that's pushed up through the international processes. And one of the examples that I like to use is in the aviation process, ICAO makes the standards. However, they start with guidance material. That is generated by expert groups with industry input. And before they get to the place where the governments have to agree, that guidance material has been issued and is being utilized in an international capacity. That makes agreement as a standard a lot easier if you start with this sort of exporting best practices. And that can be an industry-driven approach that is endorsed by governments. But once it is created by governments, I think you bring in a lot of political debate that slows progress.
Technical question around there.
Hi, I'm Dan from MIT. I had a question for Dr. Skinner. For the CubeSats, it seemed like the problem that the CubeSats will have when they're all launched together is that they can't find their own satellite. So really the pain point lies with the CubeSat owners and the operators. I was wondering, you mentioned that a lot of these other companies are starting to might need to do IRAD funding to develop these technologies to figure out which is which and what can go on these CubeSats to make them identifiable. But it seems like really the CubeSat owners should be the ones who should look out for these technologies. So I was wondering if there are, now that we've had so many of these launches, mass launches, and we've seen these pain points come up and up again, do you see that these either companies or schools, when they're launching these things, attach things like this on their satellites? Thank you.
Well, I think the problem is that it's a shared problem, and some of the burden falls on the government, the regulators, because they can't do things. And Doug Lavero's daughter's middle school's CubeSat probably doesn't have the IRAD funding to be able to do that, or even the recognition that this could be a problem. So I think that's why it's a complicated problem, and it's a threaded solution, if you would, that it has to happen simultaneously on many fronts. And who's to say which ones are the best? That's why we're doing the tech demo, to say, okay, here's 4 or 5 that work now. And we'd like to expand that space of solutions that could be available so that you can pick from a large menu of what would work. But you also need a regulatory stick, if you would, to make sure that, hey, you need to do this. And that's why it all plays together in that regard.
For anyone who could answer. It seems to me that onboard automated collision avoidance software may be too premature to use right now if you don't know what the rules are to build into that program. Can anyone talk to AI onboard collision avoidance? Thank you.
That also manufactures self-driving cars? You answered your own question.
And it rhymes with race wrecks.
If I could add to that a little bit. Sure. One of the problems you create is a mixed operating environment. That if you don't have the rules and you have onboard AI that will make the avoidance maneuver determination, how is that information shared with the other object? And that's where you can create a conflict. And we have the same issue as with self-driving cars. If all the cars are self-driving, it's a much safer system. But how do you transition into an environment when you have mixed levels of equipage and participation and share enough information so that the non-participant can take the correct action to respond to the AI action?
It is possible to automate stupidity.
So I think I guess for anyone who wants to chime in on the answer, I think kind of a common thread underneath kind of all of the presentations is kind of this mapping of information from the data that is collected, going through the processes to inform the owner-operators, excuse me, what to do in the event that bad things may be happening in the future, right? And so we're predicting these uncertain future states, but to what degree have we quantified just how under-observed LEO is to be able to have, say, linear and Gaussian distributions, or things that the type of 1 in 100, or these variations in opinion on what to even do in the event we've quantified these risks in the future are there. By some of the assessments that we've done and are internally thinking about are just, you kind of need to oversample these motions. And when we start talking about objects that are bricks, as Mark pointed out, most of these things don't maneuver today. The vast majority of the traffic that's coming is going to maneuver, and quite frequently, and hopefully in a coordinated way and toward a reference orbit, but it's going to maneuver with some sort of high frequency, uncertain injections into that motion. So one of the things I haven't heard folks say, whether it's in their testimony to folks recently or whatever, is how much more data, how much more coverage do we need to be able to keep up with these variations that are coming? Because it seems like all of these processes are based on an insufficiency of information, whether it's to share or in general.
So I would say, going along with that black box thing, we had a meeting with an operator of a small LEO constellation, and the point being that you should make sure that your GPS coordinates are transmitted even in the event that your main payload fails, because you've got your radio going. So that if the object is self-reporting and can do that at the hertz or sub-hertz even level, then even if it's maneuvering, you have much better. JPL, Minor Planet Center, and others have figured this out a long time ago. This is not an unsolvable problem.
Thank you very much. With that, we need to conclude because we have a break. So let's give a round of applause, please, to